Today, we are going to learn the basic physical principles of ultrasound together. Let's get started. So, what is ultrasound? Ultrasound is sound whose frequency is above the range of human hearing. Diagnostic ultrasound is used to evaluate a patient's internal organs. Sound waves are transmitted into the body, then, because the various internal structures reflect and scatter sound differently, returning echoes can be collected and used to form an image of a structure. Sound waves consist of mechanical variations containing condensations or compressions, zones of high pressure, and rarefactions, zones of low pressure, that are transmitted through a medium. Unlike X-rays, sound is not electromagnetic. Matter must be present for sound to travel, which explains why sound cannot propagate through a vacuum. Propagation of sound is the transfer of energy, not matter, from one place to another within a medium. Some energy is also imparted to the medium. Sound is categorized according to its frequency or number of mechanical variations occurring per unit time. Human audible range, from about 20 to 20 kHz. Diagnostic ultrasound, from 1 to 20 MHz, 3 to 12 MHz being the most common range. Now, we'll move on the wave terminology. The characteristics of a sound wave can be described by the following parameters. Period t, the time taken for a particle in the medium through which the wave is traveling to make one complete oscillation about its rest position. Frequency, f, the number of cycles per second performed by the particles of the medium in response to a wave passing through it. Wavelength, the distance between two consecutive, identical positions and the pressure wave, e.g. between two compressions or between two rarefactions. Velocity, c, speed of sound with direction specified. When a sound wave travels through any medium, it is certain parameters of that medium which determine the speed of sound propagation. These determining factors are density and compressibility. Therefore, speed of sound is a characteristic of each material through which sound travels. For example, air 330 meters per second, metal 5,000 meters per second, pure water 1430 meters per second. Speed of sound in various organs of the body also differs, like the table below. In practical term, an average speed for soft tissue is taken to be 1,540 meters sec. Amplitude, A, maximum variation of an acoustic variable. Thus amplitude is a measure of the degree of change within a medium when a sound wave passes through it. Power, W, the rate at which work is done or the rate of flow of energy through a given area. Intensity, I, power per unit area. Intensity is expressed in milliwatts per square centimeter, watt cm2. The example of sunlight shining on wood shavings is often used to illustrate this phenomenon. Piezoelectric effect. Artificially grown crystals are commonly used for modern transducers and are treated with high temperatures and strong electric fields to produce the piezoelectric properties necessary to generate sound waves. The principle of piezoelectricity is central to the production of ultrasound beams and states that some materials produce a voltage when deformed by an applied pressure and produce a pressure when deformed by an applied voltage. Thus, when a voltage is applied to the faces of a crystal, it expands or contracts, depending upon the polarity of the voltage applied. The crystal then resonates, converting electricity to ultrasound. Conversely, when the crystal receives an echo, the sound deforms the crystal and a voltage is produced on its faces. Basic transducers. Simply stated, the basic transducer consists of three parts: the acoustic insulator, the piezoelectric crystals, the backing material, and other components. These are connected to the ultrasound system from power supply by electrical wiring. Multi-element transducers. Most real-time transducers use many small crystal elements for the formation of each pulse. These form a line of elements, and the transducers are known as linear array transducers. The wavefronts from each element combine to form a single wavefront. This is known as Huygens principle. Each individual element is acoustically and electrically isolated, allowing flexibility in beam formation. Beam profile. The shape of the ultrasound beam is important to the quality of the image it produces. The beam profile is made up of three parts: near field, Fresnel zone; far field, Fraunhofer zone; transition point, point at which near field ends and divergence begins, or the length of the near field is often termed the transition distance. All sound beams are three-dimensional. The near field is the part of the beam useful for imaging purposes. However, this can be quite large in area, depending on the diameter of the crystal. Imaging requires a very narrow beam to produce high-resolution diagnosis. Diffraction pattern. A beam profile of a simple transducer obtained by plotting the maximum pressure amplitude appears as in the diagram below and shows that the energy is not confined to a single lobe but radiates off at various angles to the transducer face as off-axis energy. These off-axis areas are called side lobes. All side lobes are three-dimensional and surround the primary beam. Array transducers also generate grating lobes, which are defined as additional, weaker beams of sound energy traveling out in different directions from the primary beam as a result of the multi-element structure of transducer arrays. Resolution. Resolution is defined as the ability to distinguish echoes in terms of space, time or strength, and good resolution is thus critical to the production of high-quality images. Contrast resolution refers to the ability of an ultrasound system to demonstrate differentiation between tissues having different characteristics, e.g. liver, spleen. Temporal resolution is the ability of an ultrasound system to accurately show changes in the underlying anatomy over time. Spatial resolution is the ability of the ultrasound system to detect and display structures that are close together. Since an ultrasound image displays depth into the patient and width across a section of anatomy, it is therefore reasonable to consider two types of spatial resolution, axial and lateral. Axial resolution, the ability to display small targets along the path of the beam as separate entities. It is dependent upon various factors, the most important of which being the length of the pulse used to form the beam or SPL, which is determined by the number of cycles in one pulse, and the length of each cycle. The shorter the pulse length, the better the axial resolution. In fact, the axial resolution limit is defined as being 1/2 of the SPL. Axial resolution limit equals 1/2 spatial pulse length. All transducers of a particular frequency will not necessarily have the same axial resolution, since other factors such as damping levels can have an effect on the SPL. Lateral resolution, the ability to distinguish between two separate targets perpendicular to the beam path, same distance from the transducer. Lateral resolution is dependent upon the width of the ultrasound beam, that is, the wider the beam, the poorer the lateral resolution. We can see on the diagram, where the beam width is at its narrowest, the targets are separated by a distance greater than the beam width, and thus are resolved on the image. And the next one, we'll talk about the interaction of sound with tissues. As the sound beam traverses tissues within the body, various factors cause it lose energy and therefore undergo a reduction in amplitude and intensity. This loss of energy is called attenuation. There are four main processes which contribute to the attenuation of the sound beam, which are reflection, refraction, absorption, scattering. All of the above factors affect the echoes returning to the transducer, as well as the transmitted beam. Reflection. This occurs at interfaces between soft tissues of differing acoustic impedance. Reflection occurs where the interface is large relative to the wavelength of the transmitted sound. At tissue interfaces, some of the sound is reflected, and some is transmitted further into the soft tissue. The percentage of the sound reflected is dependent on the magnitude of the impedance mismatch and the angle of approach to the interface, such as soft tissue air interface 99.9% reflected, soft tissue bone 40% reflected, liver kidney 2% reflected. Specular reflections occur at large, smooth interfaces, e.g. diaphragm, organ margins. In these cases, the angle of incidence equals the angle of reflection. Refraction. Refraction is the deviation in the path of a beam occurring when the beam passes through interfaces between tissues of differing speeds of sound, when the angle of incidence to an interface is not 90 degrees. Scattering. Scattering occurs at interfaces within the sound beam path. The scatter pattern relies on the size of the interface relative to the wavelength of the sound. Interface much larger than wavelength reflection. Interface equal in size to wavelength scatter. Absorption. Transfer of some of the energy of the beam to the material through which the sound is traveling. Absorption increases with frequency. Absorption produces a heating effect. We will discuss the three most popular types of transducers. The active elements of a curved array or convex array transducer are arranged in a curved line. This creates a sector shape image, and the large face or aperture produces a wide near-field image. You will see a broad view near the transducer surface and deeper within the body. This makes curved array transducers popular for scanning the abdomen or fetus, where a large field of view is important. A phased array's transducer elements are arranged in a row, and the face or aperture is fairly small. The elements are steered electronically to produce a pie-shaped image. The near-field image quality is typically not as good as convex array, because there are fewer elements. The smaller footprint is able to access smaller imaging windows, such as cardiac images between ribs. The active elements in a linear array are arranged in a straight line and typically not steered. This results in evenly spaced beams and the best resolution. Higher frequencies are usually used in linear transducers, which works well for vascular and superficial soft tissue studies. Ultrasound systems operate on the basis of certain assumptions relating to the interaction of the sound beam with soft tissue interfaces. These assumptions are often incorrect, resulting in artifactual echoes with the display. The list below describes, in simplistic form, some of the common artifacts, some of which offer useful diagnostic information. Acoustic shadowing. If the proportion of the beam energy attenuated at a given interface is high, little sound will be transmitted deeper than the interface, and then echoes will not be received from tissue deep to the interface. When this occurs, an acoustic shadow is produced. Acoustic enhancement. Acoustic enhancement is an attenuation phenomenon, resulting in an area of increased brightness, amplitude, in the display relative to echoes from adjacent similar tissue. Edge shadowing. Commonly seen deep to the edges of rounded structures, when the velocity of sound in the rounded structure is different from that of the surrounding tissue. This results from a combination of reflection and refraction, occurring at the edge of rounded structures. Reverberation artifact. The multiple representations in the display of the same interface. They occur because of repeated reflections of sound between two interfaces, and are usually generated by high-level mismatch interfaces, when the echo amplitude is very high. Beam width effects. This group of artifacts can cause much difficulty to the beginner, in that they display echoes generated from the edge of the beam, as though they were generated from the central axis of the beam. These echoes are therefore incorrectly placed in the image and can give rise to pseudopathology. This group of artifacts includes beam width, side lobe, grating lobe, slice thickness, velocity artifacts. This group of artifacts occurs because various tissues have velocities different from the assumed 1,540 meters per second, which results in incorrect placement of echoes in the display. The two main types in this group are inaccurate depth calculation effects, refraction effects, mirror image, structures displayed twice, with one being a mirror of the other. These occur where there is a strong specular reflector, which acts as a mirror. Multipath. The placement of echoes in the display is based on the assumption that they return directly to the transducer after reflection, but this is not always the case. Echoes can be reflected and refracted. The component of the echo that is reflected can then reflect off a second interface before returning. This results in additional path length and time. The second echo is therefore displayed deeper than the first, along the same line of sight. In order to solve these artifacts' echoes, we need to follow the protocol below. First, turn down the gain. Secondly, alter angulation of probe and watch the effect on the artifact. Thirdly, scan in two planes. Fourthly, move the patient. Fifth, make the patient uses different breathing maneuvers. To finish, change transducer frequency. Each image could be improved in order to fit to the goal of the ultrasound application. In the table below, you could find some parameters which are used to optimize these images. First, let's talk about the transmission power, which regulates the amount of energy exciting the crystal, and therefore the strength of the ultrasound beam. By increasing it, we will increase the depth penetration and so the exposure. So, we will set it to respect a LARA rule. Depth of field also plays a prominent part in ultrasound application. A big depth of field will be chosen to study deep structures and a smaller one for superficial structures. Focus is another important parameter to optimize image. Today transducers could have more than one focus point, which will permit to expand the focal zone, but therefore decrease the frame rate. TGC means time gain compensation, and it's a gain applied only to deep echoes, as they are weaker than echoes from superficial structures. This gain will vary with transducer frequency, organ or system being imaged, and body habitus type being imaged. Let's now talk about the overall gain. If we increase it, we won't increase the exposure, but the histogram, and so in some case the saturation, which will be bad for the contrast. The dynamic range refers to the range of echoes from strong to weak available to be displayed on the monitor at a particular time. Increasing dynamic range gives a wider range of grays and decreases contrast. Furthermore, right zoom affects image quality, because the line density in pixels unit area are increased. The consequence of these benefits is a decreased field of view. Moreover, frame averaging, sometimes called persistence or smoothing, allows the accumulation of echo information over two or more frames. Increasing the amount of frame averaging can enhance subtle textural differences, but can cause blurring of the image and will result in a reduction in effective frame rate. Sign memory is the storage of several previous image frames on system freeze. Saved sequence of frames can be reviewed at will, manipulated and imaged, which can be particularly useful when scanning uncooperative patient like baby. B-mode color is a mode which permits to choose the color map and, for example, use color map, where small changes are more visible for humans. Frequency will influence resolution and penetration. So, a low frequency will give poor resolution and good penetration. The last parameter is the angle of influence. Indeed, the largest reflection of sound will occur at 90 degrees to an interface, therefore, the best images will result from a sound beam projected at 90 degrees to the main area of interest. Now, let's talk about color Doppler. The basis of all color and spectral Doppler physics is encompassed in the Doppler equation. The detected Doppler frequency shift delta F equal 2 times the initial frequency multiplied by the velocity of moving blood and by the cosine of the detected Doppler frequency shift divided by the speed of sound in tissue. We can notice that the angle is almost the only thing to change, and so when the angle of incidence is perpendicular to the blood vessel, the flow is not detected well, and if the ultrasound beam is parallel to the vessel, you get maximum flow detection. We can also modify the initial frequency, increase the frequency shift, for example, to detect the low velocities which will produce small frequency shifts. Now we know what is Doppler effect, but how we can measure it? We have two possibilities to measure Doppler effect. First, use continuous wave Doppler, where the transducer includes a continuous wave generator and a receiver that detects the change in frequency, Doppler shift, which results from reflector motion. The advantages of this transducer are an excellent detection of high-velocity flows and no aliasing limits, and the disadvantages are the fact there is a spectral broadening and there is not a range gate location. Secondly, we can use pulsed wave Doppler. Pulsed wave transducer assembly functions both as a transmitter and a receiver. The receiver gate is set by the user. The upper limit of the Doppler shifts which can be detected by a pulse Doppler system is equal to 1/2 of the number of pulses per second. When this limit is exceeded, aliasing occurs. The advantages of this transducer are a single sample volume, an accurate range location, and a quantitative spectral analysis. The only inconvenient is aliasing. Color Doppler is a display of mean frequency. Data from hundreds or thousands of sample volumes is processed using a system called autocorrelation. A very simple explanation of this is that all the frequency shift data obtained from these multiple sample volumes is analyzed for mean frequency, amplitude and turbulence. This allows us to use color Doppler information to quickly appreciate hemodynamic events occurring in the region of interest in a qualitative manner, such as existence of flow, direction of flow, but not intensity flow. When the red blood cell moves away from the transducer, the reflected frequency, FR, is lower than the transmitted frequency, FORT, and the shift is represented as blue color. Conversely, if it is moving towards the transducer, FR is higher than the FORT, and the shift is represented as red color. This can be remembered by the mnemonic BART, blue away, red towards. The size of the color box could be adjusted in white, height and depth into the patient. By reducing the width of the box, fewer color lines of sight are required. By reducing the width, each frame can be completed in much less time, therefore significantly increasing the frame rate. If the height of the box is reduced but the width is maintained, the same number of beam paths is still required, therefore, the effect on frame rate is minimal. If the depth of the color box in the patient is reduced, then for each pulse sent into the patient, the computer does not have to wait as long to receive the echoes. Each line of sight can then be completed in a shorter period of time, making the entire frame completion time somewhat faster. Frame rate therefore increases. Spectral and color Doppler controls are often not properly understood by the operator, because the modern systems available have excellent application software to set the parameters for differing flow situations within the body. However, it is necessary to understand the functions of these controls in order to optimize the system for individual, difficult cases. First control is pulse repetition frequency, also known as flow rate or scale. This determines the sampling time that is required to process the Doppler information. Since low flow must be sampled for a longer period of time to accurately analyze the information for color display, low PRF must be selected for these situations. Second control is filters such as high-pass filter, HPF, wall filter or thumb filter. Their function is to eliminate strong, low-frequency Doppler shifts arising from tissue or vessel wall motion. Third controls parameter is color and spectral Doppler invert. It simply allows the operator to make a negative spectral Doppler shift appear above the baseline, which can be helpful when interrogating a vessel from differing Doppler angles. In color, this allows arteries to be displayed in red and veins in blue, regardless of the angle of interrogation. Steering is also an important control. It allows us to place the sample volume at the best angle possible in a particular vessel and will provide directional information. However, steering also reduces the sensitivity of the system. Therefore, when small vessel flow detection is necessary, for example for thyroid or testicular studies, the ROI should not be steered, allowing optimal system sensitivity. Sensitivity is also called packet size or length and ensemble length. This is simply the number of times, and for how long, the system samples each line of sight in the ROI. Higher numbers will require longer sampling time and therefore reduce frame rate, but will result in a more homogeneous color display. Last but not least, B-scanner color priority will allow the system to overlay color information on areas of the grayscale image where there is no grayscale information. As in any other ultrasound modality, spectral and color, Doppler both have artifacts to overcome. First, aliasing is probably the most common artifact occurring in Doppler studies. It happens when the speed of the flow being examined is faster than half of the PRF set. In color, the aliasing will be displayed as the wrong color. Mirror image is the second artifact that can happen. It will present information as flow on both sides of the baseline in spectral Doppler. This can happen when the Doppler gain is set too high, or when the Doppler angle is near 90 degrees. To minimize this artifact in spectral Doppler, we can either use lower Doppler gain, either a lower Doppler angle of incidence, either reposition probe, so that cursor is between the middle and edge of the crystal. Here are some tips the operators should use to have the best echographies. First, take the transducer properly. Secondly, make the operator comfortable. Thirdly, use sufficient gel. Better more than less. Fourthly, perform a survey scan first. Fifth, choose a path of good organs to find your target. Sixth, do only small move. Seventh, use graded compression. Last but not least, use at least 2 different planes of view.